Okay, welcome to AC Generators, Transformers, and Metal Detectors. This is Review Lecture 8.3. Upon successful completion of this unit, you should be able to discuss generators, transformers, and metal detectors. All right, now we've talked about AC generators, but just sort of in passing, and I decided it might be a good idea to do a little bit more detail. A generator is a device that transforms mechanical energy into electrical energy. It is a reverse electric motor and pretty much has the same moving parts. A generator inside a hydraulic dam, such as these, uses electromagnetic induction, that's Faraday's law, to convert the mechanical energy of a spinning turbine into electrical energy. It's actually a really neat machine. Now, the basic mechanism of an alternating current generator is a conducting loop rotated in an external magnetic field. So just the opposite of a motor. A generator is a motor run in reverse. It converts mechanical energy to electrical energy. The alternating EMF induced in a coil, and they usually have many turns, this just shows one just for simplicity, of wire is made accessible by means of slip rings that are attached to the rotating loop. In other words, right here. Each end of the ring is connected to one end of the loop and is electrically connected to the rest of the generator circuit by conducting brushes against which the ring slips as the loop and ring rotate. Slip rings allow the output current and voltage to oscillate through positive and negative values sinusoidally and allows this to be brought out to the rest of the circuit. So in other words, that's the conducting path between this loop and the light bulb. Slip rings consist of circular conducting material connected to the rotor windings and insulated from the shaft. The basic advantage of alternating current, that is AC, is that as the current alternates, so does the magnetic field that surrounds the conductor. Alternating current is more readily adaptable to rotating machinery, such as generators and motors, than is non-alternating one-way direct current. And remember in the motor, in order to keep the motor running, in the DC motor, you had to reverse the current. Otherwise, the coil would go to a certain position and stop. Alternating current does that automatically. You don't have to have a special device to reverse the current. It is also easily transformed from one voltage to another using a transformer. This makes it very efficient to send energy across the country at high voltage, which is reduce current and reduce the I2R loss, but still have it in your home at a safer, lower voltage. For these reasons, Westinghouse and Tesla won the AC-DC war with Edison, and our world today is largely AC. Now here, of course, is a really simplified schematic of an AC generator. It's just a coil rotating in a magnetic field. And here are the slip rings, and of course that brings this current out to the rest of the circuit. And this is the output of this. Okay, so this is basically induced EMF in this coil as a function of time. And the peak, of course, is the peak here. And of course, it crosses zero repeatedly. It reverses in direction, reverses in polarity multiple times. And it's a sine wave. Now, phi B, which is the magnetic flux, equals A times B, where A is area of the coil and B is the magnetic field. And of course, this equals AB cosine theta. And of course, that's just the angle between the coil's normal and the magnetic field. Theta is just omega times T, where omega is the angular speed the coil is rotating at. So phi B equals AB cosine omega T. Omega is the angular frequency, and omega equals 2 pi f, and it will be in radians per second, with which the coil rotates. The induced EMF is given by Faraday's law, and the negative sign is Lenz's. And the EMF of the coil, this is for Physics 222 students, equals minus n, that's the number of turns in the coil, d phi b dt, and that equals minus nba d dt of cosine omega t. If you take the derivative of a cosine, you wind up with a sine. So the EMF of the coil is omega nba times the sine of omega t, and we can rewrite omega as 2 pi f. So the EMF of the coil, or the output of the coil, and this will be the sinusoidal output, that's this, equals 2 pi f times n times b times a times the sine of 2 pi ft. If you're a Physics 122 student and don't have this calculus, please do not despair. The only thing you really need is this part right here. Okay, but in case you want to know where it comes from, the EMF of the coil is approximately equal to minus n delta phi b delta t. And that equals minus nba delta delta t of the cosine of omega t. And if you had calculus, you would realize that that would equal omega times n times b times a times the sine of omega t. And we can rewrite that as 2 pi f times nba times the sine of 2 pi ft. Now in this formula, n is the number of turns in the coil, b is the strength of the magnetic field, a is the area of the coil. The frequency will be in hertz, that's how fast the coil is rotating, in cycles per second, hertz. And omega is the speed of the rotation in radians per second. As I mentioned before in a previous lecture, there is no consistent way of writing the AC generator equation. There are many, many different ways of writing it. And this is for a coil of area A with n turns rotating at angular speed of omega radians per second, or the frequency f in hertz, and its field of strength B. The EMF, and of course this will be the EMF that's generated, here's the waveform, over time. So the EMF is a function of time equals n times a times b times omega equals sine omega t, or it equals 2 pi f times n times b times a times the sine of 2 pi ft, or it's the amplitude times the sine of 2 pi ft. Now the amplitude is always the stuff that's in front of the sine. That is this amplitude right here. That's the height of the wave. Now, there are many different ways of writing this symbol here. And here are just a few of them. E naught and EM, E max, EP, E peak, VP, V naught, V max, VM, V peak. And there are many more of these. Now, also, often small letters are used for instantaneous values, while capital letters are used for peak or constant values, except for frequency. So, for instance, you might see this equation written like this. V of t equals capital V times the sine of 2 pi ft, where the capital V is the peak EMF, that's the amplitude, and V of t is the instantaneous time-varying value of the EMF. And they often leave the t off. Now, how do you know it's a function of time? Well, there's the time right there. How do you know it's a sine wave? Well, they tell you that right there. What's the amplitude? It's the stuff in front of the sine wave, and that will be the amplitude of the wave. Now, by no means are any of these universal conventions. There's no such thing as a universal convention here. So you just have to suffer with the rest of the electrical world. This is why I tell students you cannot memorize your way through this course. Anybody who memorizes this will probably memorize only one of these variations, and there's an infinite number of them. So what happens to a memorizer when they get on a test and somebody throws them a curve and they give them a slightly different version of the same equation? They can't do it. And they come up and they complain that they can't do it, that it wasn't the same stuff that they've studied. Well, you're supposed to learn how it works. You're in physics. You're not in memorization 101. You're in physics. You have to understand that this is a rotating coil in a magnetic field, and this is what the output looks like. This. If you don't understand that, you'll never get this stuff. And you won't do well in this class. There's a big difference between understanding how this works, that is really learning it, and just superficially memorizing it. But just be aware that there are many different ways of writing it. And I've gone over this lecture notes trying to get rid of all the different variations because I pasted these in from old lectures that I've had. And it's been a nightmare to edit this because I had about 5 of these different variations all through these notes. I tried to be consistent, but I'm probably not. Okay, so the angular frequency is omega equals 2 pi f, and that equals 2 pi over t. F is the frequency in hertz, that's cycles per second. T is the period in seconds of the source. And here, of course, is a sinusoidal waveform. It's really hard to say that. Here is the period, okay? And here is the amplitude. The voltage is positive during one half of the cycle and negative during the other half. So this means that the current in any circuit driven by an AC source is an alternating current that varies sinusoidally with time. And it changes direction. Every time it goes through this point here or through that point, it changes direction. Now, commercial electric power points in the United States use a frequency of 60 hertz. In Europe, I think it's 50. If you're in the United States and the frequency is 60 hertz, if you multiply 60 times 2 pi, you end up with 377 radians per second. So that corresponds to an angular frequency, omega, 377 radians per second. Okay, now when working with AC, and with its time-varying sinusoidal voltages and currents, we typically refer to average or RMS values for convenience. And I explained that in a previous set of slides. Go to AC. Okay, there's a set of lecture slides on AC, and that has some other information that will benefit you. For the sake of being complete here, we set up the VRMS as defined as V naught, that's the amplitude, divided by the square root of 2. IRMS, which is the current, the RMS current is I naught, that's the amplitude divided by the square root of 2. That's the definition of this. Now, voltmeters and ammeters read RMS values, which are a kind of average. And so please see the lectures on AC for more details on this and where it came about and how we derived this. Now, your typical wall outlet has a peak EMF of V naught equals plus or minus 170 volts. So that's this. This is plus 170 volts minus 170 volts. This corresponds to an average RMS EMF of 170 volts divided by the square root of 2, or 120 volts. So we've all heard of 120 volts AC. Well, that's where it comes from. And of course, you stuck a meter in your outlet, the meter would read 120 volts, provided you set it up right. This means it goes from positive 170 volts to minus 170 volts and back to positive 170 volts at a rate of 60 times per second. So it does this whole waveform right here, 60 times a second. So we have an example here, an AC generator. A coil with an area of 2 square meters rotates in a 0.01 Tesla magnetic field at a frequency of 60 hertz. How many turns are needed to generate a peak voltage or EMF of 160 volts? What voltage would a voltmeter read? Well, the voltmeter is going to read the EMF value, and that's one of the knowns, okay? And the area the area is 2 square meters. You write down the knowns, put everything in SI. The magnetic field is 0.010 Tesla. The frequency is 60 hertz. The peak voltage, which we're going to call V naught, is 160 volts. The voltmeter reads the RMS value. The unknown, we need to know the number of turns, and we want the RMS value. The physics of this is an AC generator. The formula is V naught equals omega A Bn times the sine of omega t. Omega, of course, is 2 pi f, and VRMS equals V naught divided by the square root of 2. So V naught is omega times A times B times N. That's just this part of the generator equation. That's the amplitude. N, which is the number of turns, which what we're looking for, is the amplitude V naught divided by 2 pi f, that's the frequency, times across the area of the coil, times the magnetic field. And now we can plug our number in, okay? So now we have N equals 160 volts, that's the amplitude, divided by 2 pi times the frequency of 60 hertz, times 2.0 square meters, that's the area, times the magnetic field of 0.010 Tesla. So you end up needing 21 turns to generate that peak voltage. The RMS is just the peak divided by the square root of 2, which is 160 volts divided by the square root of 2, is 113 volts. If you stuck a voltmeter across the output of that generator, or a circuit that's connected to it, you would read 113 volts, because that's what a voltmeter reads. A generator has a coil of wire rotating a magnetic field. If the rotation rate increases, how's the maximum voltage output of the generator affected? So how's the amplitude of the output? Well, if you look here, the amplitude is proportional to the speed. Okay, so if you double the speed, it will double the amplitude. So it will increase it. Okay, now mutual induction. Now we normally don't cover this much, but it's kind of cool because when we talk about transformers. Now, when coils share magnetic fields, interesting things happen. And one of the interesting things is mutual inductance. A change in current in one coil, that's coil number 1, will induce a current in the second coil. And it doesn't matter which one you change. If you change the current in this coil, it'll induce an EMF in the other coil. So E2 is going to be minus M21 times DI1 dt, or approximately, for those who don't have calculus, minus M21 delta I1 delta T. The mutual inductance M of coil 2 with respect to coil 1 is defined by M21 equals N2, that's the number of turns in coil 2, times the flux that they share, that's Phi21, divided by the current in coil 1. Now, it turns out this is only really set up by the way the coils are connected together, how close they are together, so how much flux they share, and the current in one of the coils. So a transformer, which is the next topic, is an example of this on steroids. Okay, so we have two coils. This is coil 1 and coil 2, and they share a magnetic field by being close to each other. And if coil 1 and coil 2 are near each other, a change in current in either coil can induce an EMF in the other because they're sharing a common magnetic field. The magnetic field B1 in coil 1, produced by current I1 in coil 1, extends through coil 2. So they have a mutual induction. If I1 is varied by, say, changing the resistance here, an EMF is induced in coil 2. And current would register on this meter here. The coils share this common magnetic field and a common mutual induction. And it doesn't matter which one is doing the changing, as long as they both share this common magnetic field, M21 equals M12, and that equals M. So E1 will be equal to minus M di2 dt, or approximately equal to minus M delta I2 delta T. E2 equal to minus M di1 dt, and approximately equal to minus M delta I1 delta T. The minus sign comes from Lenz's law to remind us that you cannot violate conservation of energy. You can see what's going on here. Look at this. Remember we talked about parallel plate capacitors and you didn't want to have fringing electric fields? Well, this is just as bad. This is a fringing magnetic field. You want all this magnetic field in the coil because you want this to be a maximum effect. You want this Phi21 to be completely inside the coils. Okay, not outside the coils, inside the coils. So how do we do that? Well, the simplest way to do that is to put the coils as close together as possible. In fact, they actually wind them together. Even better than that, you stick ferromagnetic material in the coil, and you wrap both coils around a common iron core to enhance this effect to make an efficient transformer, because this is a transformer. Okay, so a transformer is connected to a source, which sends an alternating EMF VP through the primary coil. VP is the EMF of the primary. This causes an oscillating magnetic flux in the core and in the secondary coil by induction, and hence an induced EMF VS that appears in the secondary, across the secondary coil. The ratio of electric potential V to number of turns remains constant in ideal transformer. In ideal transformers, there is no flux leakage or loss between the coils and no internal resistance or other losses. So the ideal transformer, we'll explain this later, is VP over NP equals VS over NS, and that's constant. The primary is the side that's connected to the source. The secondary is the side that's connected to the load. Now, a step-up transformer with NS is much greater than NP and VS is much greater than VP can boost the voltage of a generator up to several 100,000 volts for efficient transmission. So the generator might be putting out only 2,000 volts. You're going to be delivering this power over a very long transmission line. And remember, R equals rho L over A. R is proportional to L. Because guess what? If you use a high current, you got I squared R loss. It's I squared. The power is equal to V times I. So there's two ways of getting high power. And you want to use high power because you're going to transmit over a long distance. You want to get as much through the lines to the customer as possible. You don't want to have anything get lost in the lines. So power equals V times I. And you need high V, low I to reduce this. So you want high V, low I. And that's what this machine does. It has no moving parts. It just sits there. It's just two coils connected to a common iron core. Can't be any simpler than that. The generator generates maybe 2,000 volts. And then we have one of these substations. Here's a picture of a substation. It's usually things with a high chain link fence around them, and the signs all over them says danger, high voltage, keep out, and the ribbon wire on top keep people from getting into these. This is not a good place. You don't want to touch these. You generate the power at 2,000 volts, and you hop it up to one of these, to a step-up transformer. Step up means the voltage as you go through the transformer from the primary to the secondary increases. So maybe 2,000 volts gets jacked up to 36,000 volts. The high power lines in my backyard are 36,000 volts. That's Consumer Power's highest voltage transmission line. That's their main line. But you don't want that in your house. Nobody wants 36,000 volts in their house. It's dangerous as hell. So what they do then is they run it to another substation. And they have step-down transformers there. And they take that 36,000 volts, and they maybe drop it down to 14.5 kilovolts. My street has 14.5 kilovolts on it. And then they run it to all the different houses on the street. So it's a little sub-circuit. Okay, and there'll be a couple breakers in that circuit, and every house takes off that circuit. Now, but you still don't want 14.5 kilovolts in your house because it's still damn dangerous. So what they do then is they have another transformer. It's another step-down transformer. And it takes that 14.5 kilovolts and drops it down to 240. And that transformer is the one that's up on the telephone pole outside my house. And my neighbor and I share that one transformer. That's because the low voltage is safer inside the homes and workplaces, but it's more efficient to transmit energy over long distances at high voltages. Now, why don't they use a lot of little generators and little power stations? Well, it's not very efficient to do that. There's an economy of scale. And nobody wants a generating station in their backyard. It wouldn't bother me any, but most people are not me. So there's also a third kind of transformer. It's called an isolation transformer. The number of turns in the secondary equals the number of turns in the primary, and the voltage in the secondary equals the voltage in the primary. This is used to filter out or isolate sensitive circuits from unwanted electrical contamination. So if you have dirty power, something that's got maybe DC on it in addition to AC, and you don't want the DC, you run it through a transformer. Transformers don't pass DC, so they'll filter it out. And they're used in filtering circuits. Now, an AC transformer consists of two coils of wire that are usually wound around a common core of iron. The side connected to the input AC source is called the primary, and it says NP turns and VP across it. The other side is connected to the load. In this case, we represent that by a load resistor R. And this is called the secondary and has NS turns and VS across it. The core is used to enhance the magnetic flux, and in this case, to provide a medium for the flux to pass from one coil to the other with minimum field leakage losses. What we don't want to have in a core is this, with all this fringing. We want to keep all the magnetic field inside the core, none of it outside, because we're going to see why that is in a minute. Okay, now remember we talked about Faraday's law, and we talked about eddy currents. Eddy currents appear inside any conductor that's in a changing magnetic field, which is what you have here. You've got this iron core that's a conductor inside a changing magnetic field. So this will be full of little eddy currents. And eddy currents are basically currents, and you've got resistance in the conductor. So you have I squared R losses going on here in the transformer, which is undesirable for two reasons. Number one, it heats the transformer up and makes it run hot. And number two, it wastes the input power that could come out of the output side. They fix this by slicing the iron core up into thin layers, and they glue the layers together with insulators. And that keeps the eddy currents, which like to flow this way through the iron core, from building up. It keeps them physically small, so they can't build up and become large I squared R losses. So the eddy current losses are minimized by using a laminated core. Now we're going to prove the transformer equations we had a couple slides back. We're going to assume an ideal transformer. That's one in which the energy losses in the winding in the core are zero. Typical transformers have power efficiencies of 90 to over 99%. The big ones in the substations, the power company does not want to be wasting anything heating that transformer. Now the voltage across the primary coil is Vp equals Np or minus Np. This is, of course, reminding us that the conservation energy is not violated. So there's Mr. Lenz again. So Vp equals minus Np d phi b dt. Or if you don't have the calculus, it's approximately equal to minus Np times the time rate of change of the magnetic flux in the coil. The voltage across the secondary coil is Vs equals minus Ns d phi b dt, and that's approximately equal to minus S delta phi b delta t. All the magnetic flux in one coil is shared by the second one. So d phi b dt is the same for both coils. So this means there's no flux leakage, so the rate of flux change is the same for both coils, and it's deliberately designed to be that way. So then we can eliminate that. We can equate these things and eliminate it from the equation. And when we do that, for an ideal transformer that's no flux leakage or loss, the voltage is related by the number of turns in the primary divided by the number of turns in the secondary equals the voltage in the primary divided by the voltage in the secondary. And remember, the primary is the side of the transformer that's connected to the source. In other words, it's connected to the primary source. The secondary is connected to the load. Now, when Ns is greater than Np, Vs will be greater than Vp. So this means that the voltage as you go through from the primary to the secondary steps up. That's where the name comes from. So the voltage steps up from the input to the output. It's greater on the output side than it is on the input side. When you have the reverse, where Ns is less than Np, that means that Vs is less than Vp. And this is a step-down transformer because the voltage goes down when you go from the primary to the secondary. When they're equal, when Ns is equal to Np, then the transformer is referred to as an isolation transformer because Vs is equal to Vp. And these are used to isolate sensitive parts of the circuit from other parts and to filter dirty power. Now, for an ideal transformer, the power input to the primary equals the power output to the secondary because these things do not create or destroy energy. So the best you can get is the power in equals the power out. And that's equivalent to saying that the energy in equals the energy out. Now, most transformers, you actually also have some losses, but we're not going to talk about that in this class. If you did ever come across something like that, you'd include another term over here to account for the loss. So the power in the primary equals power in the secondary. And we're only going to consider pure resistances. We're not worrying about power factors here. So IPVP equals ISVS. Thus, the current is also related to the number of windings in the coil. So NP over NS equals VP over VS. That's the transformer equation. And that has to equal IS over IP. Now, notice, this is not a typo. Notice that VP over VS equals IS over IP. That's because of this. So you have a step-up transformer where VS is greater than VP. That means that IS is less than IP because this relationship has to hold. Because energy is not created in a transformer, it's only transformed. Now, the equivalent resistance of the load resistance when viewed from the primary is R equivalent equals R times the quantity NP over NS squared. So we can rewrite this as NP over NS squared equals R equivalent over R. Now, transformers also have other uses. It can be used to match resistances between the primary circuit and the load. This way, maximum power transfer can be achieved between a given power source and the load resistance. This is used in stereo and antenna terminology, and it's called impedance matching. Transformers depend upon the Faraday and Lenz Law. They don't transform or pass DC or any other non-varying input voltage. This makes them ideal for filtering out unwanted parts of dirty power that has an AC component contaminated by a DC component. Only the AC gets through because transformers require a varying voltage for the input. If you put DC in a transformer, nothing comes out, and you might even burn up the primary coil. So here's an example. Turns ratio, average power, and RMS currents. Transformer on a utility pole operates at VP equals 8.5 kilovolts on the primary side and supplies electrical energy to a number of nearby houses at Vs equals 120 volts, both quantities being RMS values. Now, if they don't tell you in a problem, assume they're RMS, and especially if they say they're being measured by a meter, they're probably RMS. Assume an ideal step-down transformer, a purely resistive load, and a power factor of unity. And of course, if it's a purely resistive load, that would be a power factor of unity. The average rate of energy consumption or dissipation in the house is served by the transformer, 78 kilowatts. What is the turns ratio, NP over NS of the transformer? What are the RMS currents in the primary and secondary of the transformer? What is the resistive load, RS, in the secondary circuit? What is the corresponding resistive load in the primary circuit? The physics of this is transformers. We write down our knowns and unknowns. The VP is 8.5 kilovolts or 85, and converted to SI, 8,500 volts. The VS is 120 volts. The power is 78,000 watts, and we want to know NP divided by NS, IP, IS, RP, and RS. But we can use the transformer equation, NP over NS equals VP over VS. We can also still use P equals IV, and we don't have to worry about a power factor because they said it was a purely resistive load. So the power is going to be V squared over R. And again, we don't have to worry about the power factor. Okay, so now we can start solving this. We have NP over NS equals VP over VS. So we have NP over NS equals 8,500 volts divided by 120 volts. That's 71. Okay, power equals I times V, or I equals power divided by V. For the secondary, we have as power over VS. For the primary, it's power over VP. And now we apply the appropriate numbers in the appropriate places. So IS is 78,000 watts divided by 120 volts, 750 amps. IP is 78,000 watts divided by 8,500 volts. It's only 9.2 amps. Now you can see, which would you rather have in the wires? This with its I squared R loss, or this with its I squared R loss? You can kind of agree that this is the reason we transmit power at high voltages, get the current low. Okay, so power equals V squared over R, R equals V squared over P. RS equals VS squared over P. This is the secondary. RP equals VP squared over P, that's the primary. So the resistance of the secondary is 120 volts squared divided by 78,000 watts. That is 0.18 ohms. The resistance of the primary is 8,500 volts squared divided by 78,000 watts. That's 930 ohms. Okay, so here we have a couple transformers. You've got 120 volts coming in. They're asking, what is the voltage across the light bulb? And we can do this because the light bulbs are pure resistance. You don't have to worry about power factor with old-fashioned light bulbs. Now, these are transformers. Whenever you talk about transformers, you're almost always counting the turns on the coils and finding ratios of turns. We're going to assume all voltages are RMS unless otherwise designated. Okay, voltages are RMS. The answer is 120 volts. The first transformer has a 2-to-1 ratio of turns, that is output to input, so the voltage doubles. But the second transformer has a 1-to-2 ratio, that's again output to input, so the voltage is halved again. So therefore the end result is the same as the original voltage. Given that the intermediate current is 1 amp, what is the current through the light bulb, which is a pure resistance? Assume all transformers are ideal and all currents and voltages are RMS. Well, the easy way to do this is to do it with a power. So we have power equals IV, and that equals 1 amp times 240, and that equals 2 amps times 120. So the correct answer is 2. Now, a 6-volt battery is connected to one side of the transformer for a long time. Compared to the voltage drop across coil A, the voltage across coil B is, okay, well, key to this, it's a battery, which is DC, and is connected to one side of the transformer for a long time. You have to have a varying voltage in the input coil to get anything out of the output coil. So the answer to that is 0. DC does not change, so the magnetic field does not change, so no EMF is induced. Now, however, if the battery is suddenly disconnected, the changing current of the primary coil induces an EMF in the secondary coil, which will cause the meter to deflect. If the rate of change is high and the turns ratio is large and the resistance in the secondary circuit is small, this EMF could be destructively large and dangerous. So the AC adapter for a laptop computer contains a transformer. The input of the adapter is 120 volts in the AC wall outlet. The output is transformer is 20 volts. What's the ratio of output to input turns? You take the number of turns in the secondary, divide them the number of turns in the primary. That equals a voltage in the secondary divided by the voltage in the primary. And they gave you these voltages. And this is just a transformer equation. So it's 20 volts divided by 120 volts, or 0.17. Okay, so as promised, here's how metal detectors work. A metal detector consists of 2 coils, a transmitter coil and a receiver coil. High-frequency AC current in the transmitter coil causes a field which induces current in the receiver coil. The net field at the receiver coil decreases when a piece of metal is inserted between the coils. Electronic circuits detect the current decrease in the receiver coil and set off an alarm. This is used by security to detect weapons because most weapons are made out of metal. Beachcombers also use them to look for coins and wedding rings. Okay, now this is another thing that you might have seen and not known exactly how it worked or even what it was. These are inductive traffic light controllers. A large area coil, maybe 20 feet long by 6 feet wide, consisting of a couple of turns of wire, is buried in the pavement between the place where a car would stop at a red light. Sensors can constantly measure the inductance of the coil. When a car pulls up the intersection, it stops over the coil. The ferromagnetic iron in the car has a much higher magnetic permittivity than the air. In other words, mu Fe is much greater than mu naught. This, of course, changes the coil's inductance. The sensor senses this change and triggers the light to change. These are easy to spot. You look for a large square groove sort of filled with a rubbery waterproof compound that's been cut into the pavement. The groove is cut into the pavement and the coil is inserted and then cemented in the groove with waterproof sealing compound. Now, obviously, you don't want salt water from when they salt the streets in the wintertime, or even just rainwater getting into this thing, because it would corrode this and it'd be really bad. Now I use I-94 to drive home all the time. And there's a couple of big gas stations up on this intersection on I-94. It's Baker Road. And these gas stations, there's 3 of them there. They're in competition with each other, so the prices are cheap there. And it's halfway home, so it's a perfect place to stop and get gas. And they have a traffic light up there. And one night I pulled up to the traffic light. I'm sitting there at the light, and I'm starting to get kind of impatient. And the light it wouldn't turn. And I looked outside the window and I noticed that this big groove was cut in the pavement. And I thought, oh, okay, the sensor just missed my car as I pulled over it. So I backed up and pulled back over it. And I did it again and again. And of course, now I'm starting to think, hey, okay, well, the traffic light obviously really frozen. And I don't want to run the red light because that's always when a cop is watching, right? Always. So there is a right turn on red. So I made the right turn on red, turn around, went up to the gas station with the cheapest price, pulled in and stopped and walked into the store. It's a truck stop. And I walked to, they wouldn't know me in there because I'm always buying gas in there. So I walked to the person behind the counter and told them that the traffic light was out and wasn't working. And I told them how I tried to test this. And they must have reported it because the next time I went through there the next day, they'd fix the light. So there you go. I used this to help fix something. Okay, thank you.